which will give good awareness to our participants related to trends and challenges in development of the electric vehicles and hybrid electric vehicles, sir. Thank you very much, sir.
Thank you, Sridhar sir, that you invited me. Really means like it was very difficult for me to get time today because I have a class from 10 today, so I just rearranged the timing. Okay. So can I share my screen?
Yes, sir. Yes, sir. Please
Okay.
share, sir.
Just a moment, sir. Just a moment.
मेरा नाम आया था पीसी कनेक्ट करना था आकांक्षा
अभी क्लास के बाद 11 बजे के 11 बजे हाँ ओके good morning to all. So because this is just a keynote, so I think I have very limited time, around 15 minutes, just to discuss the different possibilities with the electric vehicle system. So just the topic what I have given that is electric vehicle system, then charging, the grid interaction, onboard and offboard energy management. So these are all the different key areas which we need to address or study and work with when we need to electrify the electric vehicle. So let me first let you know that what exactly is an electric vehicle. So from the definition point of view, you will see that if we give the final tractive power to a vehicle in a vehicle through an electric motor, then it will be an electric vehicle. Okay, that doesn't matter from where you get the energy. You can receive the energy from onboard IC engine. You can receive energy from onboard battery sources, battery, fuel cell, etc. So, but the thing here is that if suppose that you have only onboard sources, then it is termed as pure electric vehicle or battery electric vehicle. Maybe like you will be using only fuel cells to power your vehicle. So then it will be a fuel cell electric vehicle system. Now, suppose that you have both IC engine or any of these DC sources such as battery, fuel cell, photovoltaic panel, then it will be termed as a hybrid electric vehicle. Then why we are going for electric vehicle? Simple intention is that we want to improve the performance of the vehicle, and at the same time, we also want to reduce the emission. That's why we are going for the electric vehicle. This is from the definition point of view. So when you look into the system of an electric vehicle, you will find that overall system we can divide into, you can see that supply system, traction system, control and monitoring system, then charging infrastructure. So in traction system, you will have a traction motor, which could be a permanent magnet synchronous machine. It could be induction motor, it could be DC motor. Okay. So, but when you are having an AC motor like permanent magnet synchronous machine or induction motor, switch reluctance motor, synchronous reluctance motor, then in that case, you need an AC supply. So for that, you have to use a voltage source converter. So a traction motor system is having traction motor and a voltage source inverter. Then we have onboard supply also. So you can have onboard battery, photovoltaic panel, fuel cell. These are energy sources. Then, but these energy sources can run your vehicle for a longer duration of time with a nominal current. Means let's say that your vehicle need 50 ampere of current to run it continuously. Then it will be a nominal current. Okay, but the moment you want to accelerate your vehicle, so at that time you need 2 times higher current. So that is 100 ampere of current. So these energy sources will not be efficiently able to give you that higher current. So what to do then? So we look for any other source, other sources which can support these energy sources. So those are what? Those ultra capacitor and flywheel. Okay, they can deliver you very high current, but for a very short duration of time. So those are power sources. So you will see that in supply system, you will have either only batteries, or when you are going to use the power sources, then you will have a combination of batteries and these power sources, maybe ultra capacitor or flywheel. Okay, and of course, like when you are going to integrate these different sources into the vehicle, then in that case, you need some power electronic arrangement. to make the optimal power flow and integrate your low voltage device, for example, like photovoltaic panel is there, or ultra capacitor is there, to the high voltage DC link. So generally, you will see that for light electric vehicles, the voltage is 48 volt, 60 volt, 72 volt, this DC link bus voltage. In car, etc., you will see that they go for 72 volt, 320 volt, 340, 350, like this voltage levels. Okay. Then onboard system, we have control and monitoring. So in control and monitoring system, basically it monitors the state of whole of the system, so that it can ensure the proper functioning of traction system, supply system, all those things. And also at that time, what the reference you are going to give, like say speed or torque, what you want, it should be able to provide you. So this is what the responsibility of control and monitoring system. Then charging infrastructure, this is the charging system, what we are explaining, seeing here. So it can be your onboard charger or offboard charger. Okay, why we are going for this? Because we have onboard battery, because at present we are talking about pure electric vehicle. So onboard battery is there, you run your vehicle, you lose your charge. So again, you have to charge your vehicle. So for that, we can receive the energy from the grid. Okay, and then some power electronic arrangement will be there, and that will convert AC into DC, and with that we can charge our onboard batteries. So this is about the charger what I am explaining you. But this charger, a portion of this charger can be onboard or it can be offboard. Okay. Then on the right side here, you see that here I am explaining one shown an example of a charging station. Okay. If you see that here main focus is that suppose that you go for receive the energy from the grid. You receive energy from the grid. So what is happening? That you are going to pollute one of the area where the electricity is being generated through coal, thermal power plants. But on another area, you are making clean and green because you are using their electric vehicles. So it is generally not suggested. So what we can do, we can have that dedicated solar installation or fuel sulfate charging station where you can get your vehicle charged. So, but of course, like if you are having that PV fed charging station, in that case, you need some assistant, because during the off-sun hour, you must have some support from this charging to this charging station, which can be through battery energy storage, like here what I am showing you. And then like here you see that suppose that no vehicle is getting charged, you have the surplus energy that then you can submit a portion of your energy to the grid also. So this would be like the structure of the charging onboard charging station, what you can say. So here, if you want, you can receive the energy from the grid. So it is, you say that it is PV fed, grid assisted, battery energy supported charging station. So then these are some examples like what we developed in our lab. Like this was the electric car together with this is a student project, then the bike, and these two with I worked in past, a cycle and these cars. This is like if you look into the vehicle, you will find that you have a battery. Then let's say that this is an example what you see that the two motors are being used. So here you see that the motor is part of the wheel itself. So this is called in-wheel motor or hub motor. So in this vehicle, that Biro, you have two wheel motors, you see, okay, and the two independent voltage source inverters are there, which are receiving energy from the DC bus, which is formed by the battery. Okay, then as I explained you that sometimes what happens that these battery, fuel cell, photovoltaic panel, these are energy sources. So with this, you will be able to run your vehicle for the longer duration of time, but you will not be able to efficiently support for the transients like acceleration, then regeneration, all those things. So we need to go for the mixed energy storage system or mixed supply system, we say. So just you see that why we go for this, like here, take an example of hydrogen fuel cell. So it is a higher energy density. Means you can run your vehicle for a longer duration of time, but the power density is very low. Okay, so means you will not be able to support the acceleration, etc. But on the other side, ultra capacitor, you see that it has high power density but low energy density. Means it can meet your requirement of high current during the acceleration. It can recover the energy efficiently, but it will not be able to run your vehicle for that longer duration. But when you mix these two, then you have a supply system here, you see like this, which will be able to ensure the longer duration run as well as good performance during the acceleration and the regeneration. And with this, in fact, you extend the life of your energy source also. So different sources, you see that it is available: battery, hydrogen, this is hydrogen tank, then hydrogen fuel cell, PV panel, ultra capacitors. So, and here you see that that layout what I have drawn, that's a battery fuel cell PV, and then it is the direct line, this one. Okay, but here you see that ultra capacitor is connected with a high voltage DC bus. Here, you interesting thing is that this ultra capacitor, the selection what you will be doing, it will have the same voltage level at this bus. Why? Because its intention is to contribute the current what you want to meet during the transit. Means, let's say that 100 ampere current is requirement and nominal current is 50 ampere. So extra 50 ampere current will be delivered by this ultra capacitor. So by this way, you will be able to protect your battery also from the ripples, which affects the life of the battery. Okay, and so you see that this is an example of a mixed energy system with which I worked. So here on the top, you have a photovoltaic panel, on the back ultra capacitor system, and then here battery is there. Okay, and these are the related power electronics which are required to interface it. This is an example of a hydrogen powered electric cycle. So this, what you have seen earlier, that it was a battery here. Now this battery is replaced by this hydrogen fuel cell and tank, PM fuel cell, and that this is hydrogen tank. Metal hydride tank is there, and then this is a DC to DC converter, which is arrangement which is made to power this cycle. Means interface your fuel cell with the DC bus of the vehicle, so that the motor what it is here, it can be operated. And these are some other examples like where PV panel is there and the battery is available. So like this is the layout: battery, ultra capacitor, photovoltaic panel. Then like here you just, I want to see about the configurations. Suppose that you are having a vehicle. So if you see the battery, you'll find that all the batteries are connected only in series. Okay, maybe some parallel combinations can be used to increase the AH of the battery, but no boost converter or any circuital arrangement like this will be used. Why? Because if you want to use the less number of batteries of the same voltage and then boost it to the higher voltage level, then in that case you draw more current from the battery, and so to get the same performance you have to have higher ampere hour of the battery, capacity of the battery. So the moment you increase the capacity of the battery, you don't get any power to weight ratio benefit here. So that's why we don't use that. Then where we use this type of power circuital arrangement, we use for this source and that like boost converter arrangement for the cases where the output characteristic of the source varies and you need to maintain a particular operating point. Like for the case of photovoltaic panel, we need to follow this maximum power point here. So we use it. Or in case of fuel cell, we need to, when it is loaded, the voltage will be less, and when it is lightly loaded, voltage will be higher. Okay, so you need to maintain this operating point. So we need to use this type of arrangement. So this use of this boost converter arrangement or bidirectional DC to DC converter arrangement helps us in interfacing such type of sources whose output characteristics are variable in nature, one, or second, we want to provide some assistance during the acceleration and regeneration. Then this is an example of battery ultra capacitor system in which you can see that the ripple is less when you support your battery during the acceleration with the ultra capacitor. So the moment you reduce the ripple, it means that the life of the battery is going to get extended. Then charging infrastructure. So battery charging, so it is basically a process in which you try to force the current into the battery. Okay. So you charge it, and then what is the fast charging? So suppose that ampere hour is the capacity of a battery, and that you define by C. So C by 10 is the normal charging, means 100 Ah battery, 10 ampere will be the normal charging. And if you give any current which is more than 10 ampere, that will be considered as faster charging. So K C by 10 means 1, 2, 3, 4 like this. You can go for 10 C by 10, means 100 Ah battery, you charge with 100 ampere, in 1 hour it will be charged like this. Okay, so this is about the charging infrastructure. Then different types of charging are there, which are conductive charging, then wireless charging, then dynamic charging, in which the coil is buried into the ground and the vehicle move over it, and then the capacitive charging. These are the different charging means. Charging can be continuous current, constant voltage, constant current, constant voltage charging, pulse, reflex, the same type of charging is possible. Okay. Then there are some issues with the charging. Let's say suppose that you are at the charging station and the capability of the panel, the source what you are using to feed the charging station is limited, like a photovoltaic panel. So in that case, there's always a problem of the regulation of the DC bus voltage. Okay, so like here you see that the moment you start connecting your loads, which are the charging loads, the bus voltage drops, which is not advisable. Okay, if it is dropping, it means that the burden on the charger will be more, means the cost of the charge is going to increase. So what we do that we can either through the control strategy or like maybe battery capacitor arrangement or battery energy storage system or flywheel arrangement. These can help you to regulate this DC bus voltage. Like here you see that in this case we are also able to see the regulation can be made like this. Okay. So some examples to the control also you can do it. Let's say power control you do. So with the help of it, it is possible that you can regulate your charger. Then okay, so then it is like you see that here we are talking about the charging, okay, operation of the motor, everything. So, but it is very important for us that we take care of the thermal constraints also. Like here, maybe like here I have like thermal constraint. So thermal constraint is basically I have used here some slides. So you see that when you charge your vehicle with a higher rate, the temperature also increases. So increase in the temperature is 50 degrees Celsius. So you cannot go beyond this one. So you have to respect. So this battery for whatever it is, you can maximum charge with, you see, between 2 and 4 around 3.75 C by 10. Means if it is 100 Ah battery, the 37 ampere you can charge it. So you have to respect the thermal constraint. So for that you need to take the effect of the temperature and everything to maintain, comment on the or to ensure your charging strategy. Like one example here I have shown. Suppose that is right side this one. Suppose that we operate our battery at 50 degrees Celsius. So maybe you will lose your battery. 50 degrees Celsius average temperature, charging, discharging all. So you will lose your battery in 12 months. But if you maintain your charging temperature, operating temperature at 40 degrees Celsius, maybe it will last for 22 months, something, or around 2 years like this one. So operating temperature plays very, very important role. So when you charge your vehicle, at that time you must take care of that this temperature. So for that you can make different cooling arrangement, etc. Like for the battery heat pipe arrangement is there. So those things can be done, and the charging process, during the charging process itself, some strategies could be there which can be used to regulate the charging process and so regulate the temperature. Like just one example I want to show you here. Time is limited. So this is the charging profile of a vehicle. So the moment you see that we increase the temperature reference, this curve moves up. You see. So what you are observing, that reason B here. This is the charge submitted over that at what rate you are going to charge your vehicle. So with the increase in the charging rate, you try to submit more and more current. But the moment you reach to a particular level, which is the set temperature, the charge submitted is to be reduced. Why? Because you have to go for the pulse charging to regulate your temperature, like here. So this is a reason where your temperature is controlled and you can operate your battery safely. And with the increase in temperature, you see that these curves can be moved up, and then you can ensure that charging at higher rate. So I think I have to conclude here itself. Then about the motors and all, you have like permanent magnet brushless DC motor, which is quite common to use. Then synchronous reluctance motor are coming up. So we should think about those motors also for the traction purpose. So anyone is having any doubt, you can ask me, or any question is there? Sorry, that actually I have another class also.
Yes,
So
sir.
I
Yes, sir.
have to,
Yes, sir. Thank you very much, sir.
yes, sir.
Dr. Ritesh, sir.
Otherwise, I
Yes,
would have explained in much detail everything.
yes, sir. We will meet in the second section, sir. That is series 2. We are going to conduct
Yes, sir.
in the coming month. At that time, we want your help, sir. Your guidance and contributions are helpful for us.
Okay, surely, sir. Surely.
Thank you for very much, sir, for your keynote to view the general awareness related to the electrical motors and charging systems. Then we'll have the fruitful interactions in future also, sir.
Surely, sir. Surely.
Thank you very much.
Thank you, sir.
Thank you very much. Thank you very much, sir.
Thank you. Thank you.
Yes, sir. Sir, please share your PPT to me, sir. You send to WhatsApp. Then if participants want, I'm going to share to them. Thank you, sir.
Thank you very much, sir. I would like to invite our senior professor, Mr. P.R. Subramanian, sir, to share his thoughts on the topic of the FDP.
Sir, good morning, sir.
Good morning, sir.
Good morning.
Good morning, sir.
Good morning to all the participants. Respected Chief Guest Dr. Ritesh Kesari, sir, and the HOD Mechanical Engineering Department, Led Institute of Engineering Technology, Dr. Satish Pujari, sir, Dr. Sridhar, sir, Professor from Mechanical Engineering Department, all the participants, once more, welcome you all. This presentation working on electrical vehicle development programs. Today, I will be just sharing with you some of the challenges which we are facing with this technology, I mean with this electrical vehicle technology in our country. We all know EVs are inevitable, and the IC vehicle technology will completely vanish, if not today, then someday for sure. In India, electric vehicles made its debut into the commercial market in the year 2019. We all know Revolt RV 400, which is still the most loved and preferred electrical bike in the market. And after RV 400, Tata launched their Nexon EV, which was the next super hit market in the EV market. And after that, with the entrance of countless EV making startups like Ola, Ather, Pure EV, Hero Electric, the EV market in India never looked back. But still, we see on records only 1.8% population who adopted EV in India till 2021, which is extremely low. However, this percentage of EV penetration is growing at a very high pace, nearly by 200% every year. With this pace of EV adoption, it is expected to achieve 30% of electric vehicles penetration till this decade. Why these numbers are too low? What are the limitations with electric vehicles that are stopping electric vehicles from going mainstream? The major challenge is the EV cost and battery cost. The cost is the most concerning point for an individual when it comes to buy an electrical vehicle. However, there are many incentives given off by government. Even after removing the discount and incentives, this becomes unaffordable. A new battery costs nearly 3/4 of the whole vehicle cost. Battery cost is going to be a pressing issue for the EV buyers because the electric vehicles are new to both market and customers. Second, poor infrastructure and range anxiety. Poor infrastructure is among the most pressing issue among people thinking to opt for electrical vehicles. Poor infrastructure does not only include a lack of charging stations, but also the lack of proper charging setup in their homes. Charging a heavier electrical car would be a major problem for any electrical car owner if he or she lacks proper setup, that is MCB, wire and earthing near their place. Another big issue is the ranging anxiety. This problem still required to be improved a lot. Presently, the average range is 150 kilometers to 200 kilometers, which is causing a cause of concern to most of the buyers. No universal charger and ecosystems. There is no standardized charger or ecosystem. Every second electrical vehicle making company has its own different charging port, which is becoming a hurdle to setting up a proper charging ecosystem. Then the temperature issues. Temperature can affect the performance of EV battery at a large extent, which makes EV inappropriate for too cold or too hot regions. I'm not speaking of what is the controls which has been put on the battery that is 50 degrees. But when I operate in extremely hot conditions like Rajasthan, or I'm operating in Kerala. Similarly, when I'm operating in too cold regions like Uttarakhand, how the battery will be able to sustain such type of a situation is a cause of concern today. Then where the temperature fluctuates beyond 50 degrees and sometimes it goes below 0 degrees in too cold climates. Second, very few academic and local skill awareness. Electrical vehicle push is necessary along with the academic awareness and importance to the students of coming generation. It's really a tedious task to find someone who can fix their issue or help when it's about electrical vehicles. In electrical vehicles today, it is not very easy to clearly identify the problem. Sometimes what happens, a problem is identified, we are making hit and trial methods. There is no clear-cut troubleshooting tree which can easily fix the problem because of the lack of awareness and poor skillness available in this area. Then less performance for ideal economy. IC engine driven vehicles are still way ahead of electrical vehicles when it comes to the performance. In order to make sure that an EV is giving the promised range, I mean whatever range it is, it becomes highly important to drive the vehicle at a lower performance and be aware of maximum use of regeneration. The question is, what is happening when it comes to the performance of the vehicle? When I have to go for a long range or thing, I'm asked to operate the vehicle electrical at a low performance by putting so many restrictions, so that whatever is the power, I should utilize it for regeneration. So this is causing a case of concern for all, I mean, EV users presently. Next, will increase the electricity demand. It is also demanding the electricity demand at a national level. It is just a matter of assuming the increment in electricity demand. When everyone in the city is using solar electricity to charge their vehicles, it will become a horrible and horrific increment in the demand for electricity. And as of now, we are majority dependent on burning fossils for generating electricity. Especially in our country, there are so many places where electricity is in short supplies. There's so many electricity holidays and all. So then in such cases, this becomes a situation of concern. Then environmental concern, even most of the charging stations are reportedly operating upon diesel-driven electricity generator. So this electricity generator is giving emission problems. So the alternative source of renewable energy sources should be set up. Servicing is in danger because what is happening, most parts are, I mean, having different strategies and different specifications. Even a small defect, it calls for complete replacing the whole setup, not as a particular part of the unit which is breaking up. These are some of the issues, which are the challenges, which during this workshop can be debated, discussed, deliberated, and the we can think of a way forward of addressing all these issues. Thank you very much.
Thank you, sir. Thank you very much for elaborating on the challenges that are involved in design and development of electric and hybrid electric vehicles. At this time, I also would like to acknowledge the presence of the other resource persons from whom we will be hearing throughout the week. I welcome all of them on behalf of the Department of Mechanical Engineering, the Indian Institute of Engineering and Technology. Ladies and gentlemen, we have now come to the end of the inaugural session. We have a few announcements, after which we will begin to hear from Mr. Avinash Kishore, General Manager of Revolt Motors. A few guidelines to help run this session smoothly for all of us. Please mute your audio and your video at all times so that it will be convenient for the speaker during his talk. During the interaction time, please use the hand raise option to ask any questions so that the host will enable you to speak. If you have any questions in between the sessions, please feel free to post it in the chat box so that I'm sure that our resource persons as well as our team would be able to address your issues. And make sure that you sit in a proper place where you have an internet connection. And one more thing is that the feedback form and the attendance form will be given at the end of each session in the WebEx meeting link only. They will not be posted in the WhatsApp groups or any other groups. And the link will also be alive only for a short time, and after which it will be taken down. And please make sure that you will be using your participant unique ID. If you do not know your participant unique ID, please check your mails. We'll send mails to everybody along with their participant unique ID. Please use that while filling these forms. So with that said, we will now be moving on towards our first session for the day. The topic for this session is Trends and Challenges in Electric Vehicle Design by Mr. Avinash Kishore, General Manager, Revolt Motors. Before I hand over the session to him, I request our convener, Dr. K. Sridhar sir, to introduce the speaker for this day and hand over the session to him. Over to you, sir.
Good morning to all the participants. Welcome to Mr. Avinash Kishore sir for accepting our invitation to deliver your lecture in spite of your busy schedule. Participants, I want to speak a few words about Mr. Avinash Kishore sir. Mr. Avinash Kishore sir presently with Revolt Motors as General Manager R&D. Sir has completed BE degree in Electrical Engineering from National Institute of Technology, Patna. MTech from Netaji Subhas Institute of Technology, Delhi University. And he received Executive Management degree from a top institute, Indian Institute of Management, Bangalore. And Sir started his career with teaching nearly for a duration of 5 years with Birla Institute of Technology, Ranchi. Then he come to the industrial field. He worked as a senior engineer related to R&D drives with EDC converted EDC Limited, Berlin, Germany. Then he worked with General Motors Technical Center India Limited, Bangalore as engineering manager. Then he contributed his services as senior manager R&D drive and automation with CG Power Industrial Solution, Bhopal. Then he worked as engineering manager, electrical and electronics hardware, Baxter Innovations and Business Solutions India, Bangalore. Then he contributed as associate director, Powertrain Hardware, Vola Electric Private Limited, Bangalore. Then he joined Revolt Motors. Now he is contributing his services as General Manager R&D, Revolt Motors. Sir has published many papers and patents, and he completed his PhD thesis also. In short time, he will be awarded with a PhD degree. It is a really great thing, sir. In spite of his busy schedule in industry, still he is contributing towards academic line. He has a good global exposure with General Motors, Michigan, visited multiple times for projects, then convert in Berlin, Germany, on-site project execution, and Yangam University, South Korea, as a visiting researcher related to power electronics lab. And he visited Singapore and Italy to present the research papers. And SAR has good exposure related to the R&D, electrical vehicles, motor controls, hardware, new product development, business manager related activities. And his main contributions are related to hybrid electrical vehicles, inverter and motor control strategies, motor control unit integration with the battery management system, vehicle control unit, DC converter, charger and other mechanical components, electrical vehicle architecture, fuel economy analysis. Definitely, sir, your presentation will helpful to all of us along with the participants to enrich our knowledge related to the trends and challenges in development of electric and hybrid electric vehicles. Thank you very much, sir, for your presence today. Please start your section, sir.
Thank you. Thank you, Sridhar sir. Am I audible to all?
Yes, sir. Yes, sir.
Okay, fine. So I'll share my screen now. Can you make me as a host or something, because I'm not able to share my screen?
Already, you are
Okay,
the
yeah.
host, sir.
So yeah, okay, fine. So now I see the time. Okay. Okay, thanks. So you see my screen?
Yes, sir.
Okay. Thank you very much, Sridhar sir, and everyone for inviting me. It's a really great opportunity to connect with the university and try to contribute. What we are doing as an industry person, how we can better collaborate with industry and academic research experts, so that we can do more and more innovations and develop more and more innovative products for customers. Okay. To start with, I believe sir has already given my introduction. So I have almost close to 20 years of experience. I started my career with as an academician, worked in BIT Misra as a professor, and there I also started working my research work. My industrial journey started in 2008. Started with converting, and then I spent 10 years with General Motors in the field of electrical and hybrid vehicles, and a few years with variable in the field of variable frequency drive with converting. Then 2 years as a medical domain, I have also worked as a hardware expert there for HD and PD machines. Very short duration with Ola Electric, and now close to sorry, it's a typo, close to 8 years, 8 months with Revolt Motors. From education, by education, I'm a engineer, electrical engineer from NIT Patna, masters in process control from Delhi University, and also I have completed recently as an executive management from IIM Bangalore. Yeah. So to start with, I have seen that Dr. Ritesh Kesari's presentation that was excellent, informative. I'll go through that just to brief. I'll be covering my session in two parts. One first part I will be covering as an overall architecture of electric vehicles. What are the components it is used, and it will be useful for everyone that what are the other components used for electric vehicles. However, because of I'm a hardware guy, I will be mostly covering hardware perspective, not as a mechanical, but feel free to ask me the question. I will try to answer. This session I would like to have a more interactive, and if you want any questions to be asked, you can stop me. I am okay to answer. Or and at the end of the presentation also, you can park your question, and I'll try to answer your question. Yeah. Because I am mostly have contributed recently in the two-wheelers. I have well experience in two-wheeler for Ola Electric and recently for Revolt Motors. So my hands-on expertise is two-wheeler. That is very recent, so that I can answer anything related with the two-wheeler electric vehicle, what is going into the India. And however, I have also contributed close to 10 years for hybrid and electric vehicles while in General Motors. I myself has contributed in some of the pioneer vehicles like the Chevy Volt, and I will be happy to answer any queries or curiosity. Please feel free to ask. Okay, so yeah, so start. So before starting, just give you the some disclaimer. Whatever I'm showing, this is completely available to the different channels. For example, ARAI website or Niti Aayog or multiple different application notes. So you can find out these materials anywhere, and also if you have any particular question, I can answer. Okay, so there is no confidential of whatever the data I'm showing, and you can take it from here. Okay, okay, so let's start here. So that electric vehicle is growing. It's not only growing, it's pushed by the government of India and overall globally, so that we have to their aim is to do electrification, you can say, as a completely moving from IC engine or fuel based engine to completely to electric. That is not only electric, it is also part of fuel cell. Okay, so their target is to by 2050 it should be close to 100% electrifying all over world, and India is not behind. India is also doing that. So to push it, there are multiple policies and multiple programs and policies has been come from the government. If you see, because of this push, if you see that the electric vehicle is growing very rapidly, and this data it's showing that next 5 year, if you see, our CAGR is 28.93%. That means this is the growth rate for only electric vehicle in India, right? For example, some of the major players who is already playing to the market, it is Suzuki, Toyota, Tata, Mahindra, and many others. As a global market, if you see that if we talk about India right now, India is already having 7,000 USD million. It's already in 2021, and it's expected to reach by 30,000 USD million, and that is a huge. Like I said, as a organization from the government, one of the mission that's called the National Electric Mobility Mission Plan, and to have the faster adoption, you might have heard about FAME 1 and FAME 2 discount. This discount is kind of given by government, and they are pushing really heavy money so that it is easy to adopt by the customer. Why it needed? Because the cost of electric vehicles is right now it is high because of various components, for example battery and other parts. So to afford into by the common people, so that we can compete with the existing fuel engine, IC engine vehicles, government is giving a discount that is named as a FAME 1, and right now we are having FAME 2 discount, so that this can be affordable by the common people, and hence is in the interest of manufacturer, it can move forward, right? So just example, like let's say if you are buying an electric vehicle, let's say electric scooter, so whatever the price you are getting, or you can see you are getting into in your hand, whatever you are paying, that exactly not received by the manufacturer. They are receiving much higher than what you are paying, and because of the FAME 2 discount, government of India is paying certain amount to the manufacturer to compensate the gap. Okay, so if you see the company profiles I have just collected here, the four wheelers, these are the companies which is kind of really moving high. For example, Tata Motors, Mahindra, Hyundai, MG Motor, BMW, Mercedes, Skoda. Three-wheelers is Giporia, Terra, Piaggio, Kinetic Energy. Two-wheelers, you might have heard already, where I'm working here, Revolt Motors. Apart from that, we have Pure Energy, Pure EV, Torque Motors. This is coming with a bike. Ampere Vehicles, scooter. Okinawa, this is kind of selling right now highest number of vehicles, two-wheelers right now in India. Then Ather, that is kind of having a really good two-wheeler electric. Hero, Bajaj, Ola, and TVS, and many more. If you just Google it, how many electric two-wheelers into the India, there are more than what I'm showing. So these are the top 10 right now into the Indian market. Okay, so going forward, what interest as a power electronics? What may be the typical rating of the two-wheelers or four-wheelers? Right. So I'll just start with two-wheelers which have the battery rating of close to 1.2 to 3.3 kilowatt hour, and battery voltage it is 48 to 72 volt. However, 48 volt is the most common voltage rating for the battery. It's adopted in, at least in India. Few customers, a few players, they are actually working with a 72 volt battery as well. Revolt Motors, my company, is one of that company that we adopt 72 volt battery. There are certain pros and cons having if you go higher voltage rating or lower voltage rating. Even if you see some of the voltage, they're also adopting 36 volt. Right? Three-wheelers, again, it's a 48 to 60, but if you see the battery capacity is higher, it is 3.6 to 8 kilowatt hour, because the motor capacity is also higher and it is used for passenger goods. Electric cars, if you talk about first generation, that means bit old. It is a 21 kilowatt hour to 72, but these days what we are having is really powerful battery, powerful cars with 30 to 8 kilowatt hour battery capacity with 350 to 500 volt. This is really high voltage system, and we are having this. Next, very brief, I would like to cover that electric two-wheeler architecture. Looks like very simple, but I would like to go little more depth into that for your interest. If you see that what is electric vehicle, and many of you are from a power electronics background, and you know that hey, looks, it's very simple. That is, we'll have the battery, and we'll have the motor. This motor should be AC motor. Okay, AC motor may be BLDC or PMSM, that is mostly adapted, and then we can have a controller, and finally just convert from DC to AC in the control manner, so that you can control the speed of the motor, and hence you can control the vehicle speed, right? And yeah, throttle, where you are kind of giving the command that what speed you want to run your vehicle, and accordingly your controller, that means it's nothing but inverter inside, it is taking control. But there are certain other components also associated here. It's like a DC-DC converters and other accessories, right? So it is not only inverter. There are multiple other power electronics components or hardware components, I can say, which is actually adding more complexity of any two-wheeler, right? So if you see the right side, we'll have the meter. Right now, if you see, many of OEMs has adopted very interactive speedometer, where you can have the touch screen and multiple other data or information it's displaying. For example, vehicle speed and chargers, charging status, SOCs, even maps you can see, and also you're putting the Android. It's almost equivalent to your smart mobile phone, that is almost displaying here. There are multiple sensors associated. We'll have battery and DC converters. Power unit drive, like I said, is a controller. This is the most powerful components of electric vehicle. Motor and the charger, right? Charger is important. There are again two type of charger. It's on-board charger and off-board charger. I will talk about. And again, these three colors, what it is showing, it is kind of three different signals. One is signal where all those components should talk with each other, so that will have a better control. That electrical power and the communication. So communication and the electrical may have the RS-485 or CAN communication. Moving forward, little bit elaborated way of this architecture. And just I am showing here right side of the electric vehicle, and this side the battery pack. So if you see, there are two voltage system, or you can say there are two DC voltage levels. Mostly, if you just take about 48-volt system, okay. So battery pack is showing 48-volt system here, but many other components that need a even lower voltage, and the common or standardized voltage, it is a 12 volt. This 12 volt is for other accessories. For example, throttle. For example, maybe multiple sensors and multiple, loads, lamp loads, throttle, like I said, other control or other small motors. So this 12 volt bus is important. And to convert this 12 volt, again, there is a DC to DC converter, which is converting 48 to 12 volt, and it is kind of supplying, power to multiple accessories of your electric vehicle. Okay, but this motor controller here, it is definitely taking the 48 volt, which is kind of driving directly the AC motor. Okay. Coming to battery management system, I'll just give you very brief about what is battery management system. When we see a battery, it is little more complex than what we understand. However, many of you might have already worked on battery management system, but I'll just give you a very brief. Uh, Battery management system, basically, it is for lithium ion, and to achieve the 48 volt or any voltage levels, we have to stack it up for all its cells. Each cell, it is peak of 4.2 volt, and depend upon the ampere hour. So each cell is having a very small ampere hour. Stacking depend upon your requirement. uh, for example, if you want to make a battery pack of 4.2 kilowatt hour or 3.7 kilowatt hour or more, the battery team, you need to stack it up, make is a parallel or series combination, and then finally you also need to make sure to have multiple other safety challenges that I will talk about. Okay, so when we say safety challenges, why battery is storing energy, and energy in term of different, you can say, charge. And if you're talking about charging and discharging, then you have to also deal with heating, right? So to control this battery management system, you have to control battery, continuously monitoring the battery. You have to provide the battery protection, and also continuously estimate the battery state of charge. So charge and discharge, that all depend. And finally, you have to make a battery management system such a way that you can safely operate the battery for your vehicle, right? So like I said, cell balancing. First, you have to understand why cell balancing is important. What will happen when the cell is not balanced, basically, right? Just one example I have shown is a two pictures. These cells are stacked up, no matter it is series or parallel. But let's take consider these all batteries are in series, right? Ideally, each and every cell should behave in the same manner with others, but it is not. Practically, it is not. Then what will happen that, let's say, one or two cells out of a stack of these 10 or 20 cells is discharged faster, or what will happen that some of the cells, when you charge it, charge very faster, and it becomes 100% only one cell, and the rest of the cells are not reached 100%. Okay, So the problem is that it is called a cell unbalancing, and there are multiple things may happen. For example, if one of the cell is discharged faster, if you see that if this is a series, this will become disconnect. This will be disconnecting because there is a no charge left. So you can say this is a complete kind of disconnection happening for other cells, right? So this is an electrical issue. Similarly, if you are charging this cell very faster, if one of the cells got charged fully, that means this is a kind of making as a disconnection or isolated, and the rest of the other cells won't get the electrical connection. Okay. So this is a electrical issue. But what is the other issues? Other issues is that if this is discharging faster, it will be having a more heat generated. Similarly, this is also having the more heat generated. And other part is that SOC or cell imbalance will happen because you need, let's say, 4.2 volt or 3.8 volt. So you need to have this 1 volt fixed voltage, and accordingly you will be doing your other controls. In case of this unbalance, there is a multiple other problem may happen. Okay. Other problem is that cell degradation, because the cell which is having the more stress, charging or discharging faster, this cell will degrade faster than other cells, and your whole battery, even if one battery is degraded or spoiled, whole battery will be kind of you can say it's spoiled until unless you open and refurbish its complete battery pack, which is practically right now not so much of feasible. Right? So this is the thing, and because of that, it is very important that you, while charging or discharging, you must balance the cell, keep monitoring that all cell is balanced, right? So what to do? The question is that while charging or discharging, how to make sure that each and every cells are balanced, right? So there are again many research are going on. I'll tell you, battery management system is right now in the field of electric vehicles a most favorite research topic across the globe, and there are multiple research is going on, different patents and papers are. So but I'm not the battery expert, and I'll be covering a very high level or very basic level of the battery management system. So how we are going to do the cell balancing? It is easy. Theoretically, measure each and every cell voltages, okay, and accordingly you measure SOC. You keep estimating the state of health each and every battery. Balance the cells. How you are balancing the cell? There I'm going to cover it. Either, let's say, if left side cell is more charged or right side cell is less charged, either you discharge this or you charge this. So make sure that this both cells are equally charged. Okay? And then finally, when these both are equally charged, you can finally get the wave. Okay. So coming to cell balancing, how you are going to balance the cell? The most common method right now, especially for two-wheelers, it is passive cell balancing, because it's a very cheap and very easy to get it. I'll just talk about left side. If you see, we have the cells stacked up. It is showing 1 to 4, and each cells is connected with a resistor. We say it's the charge resistor, along with the one MOSFET. This MOSFET is stacked up with across each and every cells, and then the controller. This controller is inside have a other architecture. This architecture will consist of different other switches and resistors. If you want to know, I'll just give you some hint. We say it's AFE, and right now there are multiple players which is actually have available with multiple AFE, which can help you to design your cell balance. Right? How it works? It all depend upon how you are switching these MOSFETs. Let's take example of cell 1. If cell 1 is having higher capacity, 10 other cells, let's say cell 2, cell 3, cell 4. So you want to discharge it. It is easy. You know that with the cell balancing or cell measurement, cell 1 is higher, right? So you have to make such an arrangement that this switch on MOSFET should be switched on. Very easy. Current will start flowing internally here, make the path from this R versus this R. The right side, if you see, there are little bit elaborated version of this picture. However, there are another resistance has been added, that is called a cell balancing resistor. So this MOSFET will be switched on till this voltage is get discharged through these resistors. Okay, take example, let's say if it is a 4.2 and the cell 2 is 4.0, so this MOSFET will be turned on till this voltage becomes 4.2 to 4.0, so that all the cells will be balanced. This is a passive cell balancing. If you see that, we are kind of wasting the energy, right? Because it is easy to do the cell balancing, but the drawback of this method is we are kind of wasting the energy, right? But this is a very easy and quicker to implement for two-wheelers, and at least in India, these are the balancing method has been used. If you talk about active cell balancing, there are multiple ways. I have just shown two methods in that. Here we are not wasting the energy. We are trying to use this energy, one of which one is having the more cell, and try to charge it adjacent cell by the combination of the different switches. Okay. Left side it is showing that we have connected multiple capacitors. Okay, and the right side, if you see that we have connected the multiple inductors. So this is called the flying capacitor method, and this is the inductive capacitor method. If you see here, the switches are number of switches are very high. Each and every cells may have the switches between these two. Okay, so this capacitor, if you see that, let's say if you are switching this switch one on this side, and if you are switching this to this side, this capacitor is actually try to balance this. Similarly, if you are switching this side, this capacitor is coming to this side. So this is the way that we do the cell balancing without wasting the energy, and same way towards the inductor. Okay, this curve is important. I believe that Professor Kesari has shown one of the curve. This curve is called the constant current, constant voltage method. This has been derived from the characteristics of the battery, and while designing the charger, this constant current, constant voltage, or you can say CCCV mode, it is important to understand the behavior of the battery. Okay, so this has been taken for one cell. If you see 4.2 volt, it is the voltage level of one cell usually, or you can say typically. When we charge it, this particular green line is SOC. SOC, that means it is all the way from 0% SOC, increasing. The way we are pushing the current, this uh, this yellow line is nothing but current. If you see that we are pushing the constant current and SOC is increasing, right? If you see close to 75 to 80 percent SOC, we are now decreasing the current in the exponential manner here, and we say that voltage is constant. So before this red line, left side, we say constant current, and off right side of this red line, we say constant voltage. So the question is that why we do this? Why not directly charging the constant current and we are done? Let's say we are having if it is a 1.5 hour and then constant voltage is slow charging for 4 hours. So if you carefully see, SOC close to 80 to 100. That means last 20% of the SOC we are taking almost 2 hours, and first 80% SOC we are taking 1.5 hour, right? The question is why we do so. The answer is that because of the battery cell capacity or safety, right? When we start charging here, battery is empty. There is no cell, no charge inside. So we can push the current. We can say higher current or higher capacity current, push it, and that's how the cell voltage is started. If we say 4.2 volt here, so for low SOC, if you see the voltage level is low, it's close to 3.5 volt. The moment we are charging it, cell voltage is increasing, and now if you see it is close to 4 or 4.1 volt here, or you can say 4.2 volt. Now battery is almost full, 80% SOC is done. So if you're pushing more and more current, you are try to push more and more energy and push more and more uh, you know uh, capacity of heat. So because of the physics of the cell, we are stressing out, and possibility of over stressing of the cell, and hence maybe thermal damage or thermal runaway of the cell is higher. And that's the reason once the cell is achieved almost 80% of SOC and close to 4 volt at the terminal voltage, we drastically reduce the charging current, and we say for 20% we do slow charging. Like if you remember that Professor Casey has talked about the C rate, okay? So we say fast charging, we say C rate of let's say 0.5 C or 0.2 C, that depend upon yourself. And then when it is almost 100% of charge or 80% of charge, we reduce the C rate and we push very less current. And even if you see close to uh, 80 or 90%, even we decrease the current to 1 amp or even sometimes milliamps. Okay. So while designing the charger or while designing the battery management system, this curve is the very important basically. Okay. One of the chart would like to show you here, that this is for global. I have taken from some of portal. If you see here, that is all four-wheeler. Battery capacity is all the way from 6.1 kilowatt hour to 100 kilowatt hour. Okay, and the power rating, that means the motor power rating is 4 kilowatt to almost close to 193 kilowatt. You can think of the battery capacity 100 kilowatt hour and the motor of close to 200 kilowatt, right? So you can, as a power electronics hardware people, you can think of how much power we are driving from the battery. But more than battery, I would like to show you the price here, right side, right? Price of the battery is very high. Mostly we use lithium ion, and there are multiple other combination of lithium ion, this LFP and others. Price of the battery is very high right now. Okay. Moving on, very brief, I'll just talk about the motor, what type of motor we use. For two-wheeler, even for four-wheeler, for two-wheeler and low capacity or low power two-wheelers, we can use BLDC motor. Usually if you see BLDC, it's kind of hub motor. That means this motor is a part of the wheel. There is no additional. This type of hub motor you might have noticed for small power two-wheelers. It is a part of the wheel. We say hub motor. PMSM motor, when we go for need for little higher torque and little higher power, we go for PMSM motor. This cannot be embedded as a part of the hub. So this motor you can use as a to drive the wheel. You have to use certain gear arrangements or belt or something that most of the OEMs are using. Comparison in the brief, why we go for, where we go for BLDC motor and where we go for PMSM motor. As a theory or architecture, both are AC motors. However, little bit of constructional difference they have, and because of that, their characteristics and their torque handling capacities are different. Little bit, not much. BLDC, you know that it's a trapezoidal back EMF because of their windings, you know. So there, how it is winded, it's like concentrated versus distributed, and because of these two windings, BLDC is actually developing, or you can say creating a back EMF which is in trapezoidal in shape versus PMSM which is in sinusoidal in shape, right? And because of that, BLDC, because of trapezoidal shape, the current ripples are a little higher as compared to PMSM motor, right? But BLDC are cost effective and PMSM is expensive. The reason is that PMSM comes with the permanent magnets inserted, and because of that it is high. So PMSM is having the higher power density because of permanent magnet motors. Efficiency is higher than BLDC motor. Hence, PMSM is suitable for higher power. When you need more power, more torque, more speed, go for PMSM. You need a little lesser power, you should go with BLDC motor. Yep. This is the Indian comparison of what we are doing right now. All the way from Aether to Hero, right? So battery capacity I have shown. I told you it's close to 2 to 3 and up to 4 kilowatt hour. If you see here, all the way 2.9, 3.24, 3.97, 3, 4.5, 3.3, 1.4. And like if you remember that I talked about the voltage levels, most of the OEMs is taking 48 voltage, 48 volt DC. Revolt motor, they are using 72 volt. Motor capacity is all again. If you see that if it is a higher kilowatt, this is a PMSM. So 6 or 3 or 8.5 kilowatt is the PMSM, and the lesser is the BLDC. However, I have noticed that Bajaj Chetak is having the 4 kilowatt BLDC. However, if you see 1 kilowatt or 1.2 kilowatt, obvious choice will be BLDC motor. Now, because of the battery capacity, we have the multiple range all the way. If you see Okinawa, because of the small motor capacity, they are kind of achieving 160 kilometers. Same for others. If you have, let's say, 3 to 4 kilowatt hour battery, you can achieve more than 100 kilometers. Right? Top speed 80 to 100. However, the lower power, if you see Hero Photon, it is 45 kilometers per hour. But Ola, which is claiming highest speed 120, 115 kilometers per hour. However, the rest of the other big players, Ether, Revolt, they are achieving close to 80 kilometers per hour. However, two-wheeler or four-wheeler, these numbers are good. 60 to 80 or 100 are kind of exciting the customers in India. 45 kilometers are a bit low. However, for the town, for small kind of, let's say, office commutation or something, this is also fine. So if you see that there are variation of specifications of different two-wheelers are available into India. This is really good. Now, if you go and want to buy the two-wheelers, you have a different range depend upon your requirement. You can find out a different range and you can go for that. And this is really good thing happening into the India. Next, coming to motor control. Like I said, this is important part. Whether it will be BLDC motor or PMSM motor. Motor controllers is, you can say, is a kind of hurt. Why I am telling hurt? There is a difference between heart and the brain. Why it is important? Because this is kind of taking the power from the battery and running the motor, and all your control strategies control strategy, that means different set of the speed. You can say speed. There are multiple other things. For example, starting of the motor, then high speed, you can say cruising, and the important is the regeneration. You want to capture the energy as a different, we say, as the opportunity charging. For example, braking or cruising, and or other way, you want to capture the energy and feed back to the battery so that you can get some more range. So these things has to be taken care by the motor controller. So your motor controller should be smart enough. This left side I'm showing is a very simple inverter technology, what you guys have already studied during your BTech or masters. So having this 6 switches, this switches may be IGBT or MOSFET, mostly for 48 volt or 72 volt system. We use MOSFETs, right? AC motors, like I said, it may be BLDC motor or PMSA motor. Then we have the feedback control. So definitely this is control is a closed loop control, where speed has been monitored using any speed sensor, encoder or whatever, and with the controller you measure all these voltages and currents, and vector control, you can say field oriented control as a commonly known. And finally, with that different PWM methodology, for example, SVPWM, space vector pulsing modulation, or anything, you can control this inverter. Simple. It's very simple, right? Right side, I'm showing one of these, inverter by ST, one of the valve board where you can use it. You can buy it and you can do some experiments. Okay. Little bit elaborated way of FOC. I'll not go through in detail, but you know that we have this DQ control, where you read each and every current in 3-phase, convert 3-phase to 2-phase. That means it is a rotating reference frame, and then convert from rotating stationary reference frame to rotating reference frame, so that alpha beta to DQ, so that your all alternating quantities become time invariant to time invariant to time invariant. It will be alternating to DC quantity, where you do all those calculations. You do the speed estimation, flux, and all those things. And finally, based upon your set point, where you are having this set point, that means what will be speed reference, and do all those PI calculations, or you can say tuning of parameters. You generate the PWM pulses to get the desired speed. Okay. So this is a closed loop controller, and this is kind of used in all two-wheelers OEMs these days. Yeah. Like I said, there is a brain and there is a heart. Motor controller we say as a heart. Why? Because this is the kind of controlling all your part, mostly in the motor, with the speed. But again, to control even motor controller, you need a brain. Electric vehicle is not only speed. There are multiple other features you need. There are multiple other safety features you need, right? And for that, you need a vehicle control unit, right? So this vehicle control unit these days, you can have multiple others, but I'll just talk about two-wheelers, right? So this vehicle control unit is constantly monitoring the system. Let's say it is connected with the battery, right? Battery may have some type of information. For example, battery temperature, SOCs, what is the range left, range calculations, all those things you want to display to the speedometer. Similarly, this is also constantly communicating with the charger, or there are multiple sensors. They have the throttle, they have the stand sensors, they have the fuel sensors, they have multiple other things, right? So this has to be taken care by the battery, vehicle control unit, and control unit can control the other parameters, right? So this is the role of vehicle control unit, and mostly in the vehicle, even in the two-wheeler, this is communicating with the CAN, right? And CAN or RS-485 is kind of communication where you constantly communicate, receive or send the information to the various other components. Okay, and they're important. It is you can say as a part of your body. It is the vein of the body. It is the most important. However, there is no intelligent part here, but it is very important. I'll tell you why. If you see that the battery or multiple other hardware components, they need to send and receive the signals, not only signals, the powers to different ways. So wiring harness and smart arrangement of wiring harness is very, very important. Okay, so that is number one. Second is that if you see that let's take example of the motor controller is having three-phase signals or three-phase power it is going through. RS-485 is having very low signal. DC-DC converter is having even less. So if you see that different combination of powers with different ratings and they are flowing to each other, right? There may be the problem of communication interface. There may be the problem of EMI EMC, right? To overcome, even your controller is smart enough to control it, but wiring harness is important because this is adding additional circuitry in your system, right? So making the wiring harness smart, it is the most important challenge of electric two-wheelers and even electric four-wheelers as well. Okay, moving on, the compliance. When you design the vehicles, I'm talking in the reference of India, you need to comply certain compliance standards, and these standards has been decided by the ARAI, Automotive Regulatory Authority of India, right? And each and every OEMs has to comply those standards. Those standards are for vehicle. They talk about EMI/EMC, they talk about safety, they talk about range, they talk about different other aspects, right? Some of the standards not limited to, let's say, AIS 004, AIS 156, or AIS 138. These are the standards. These standards are a combination of multiple other global standards, right? For example, all IEC standards depend upon what, let's say, take example of EMI EMC, right? So AIS 004, this is if you talk about EMI EMC or charger or vehicle or battery, they are talking about combination of what may be the safety standards, right? Thermal standards and everything. They also talk about qualifying criteria, and hence you have to comply that. Then only you are qualified to sell the vehicles into the Indian market. So this is the regulatory authority, ARAI, which is actually has come up with this AIS standards. Okay. Uh, if you talk about, I'll just say because I'm a hardware guy, to give you a glimpse of standards here. See here, different tests. For example, electrostatic discharge test. Let's say, however, this is not a complete thing. This is just an example. Please don't take it as a final go ahead. And I am also giving the reference standard for the IEC. Okay. So let's say talk about electrostatic discharge test. We must have this 4 kV and 8 kV direct and air discharge. Similarly, we must have this supply harmonics, right? So your duty must have this supply harmonics of 50 hertz to 2 kilohertz. And also, so these are the supply voltage and supply. This is this is in the case of the charger basically. So please don't take it as a complete vehicle. Okay. So if we talk about supply voltage harmonics or supply voltage, this is in the case of charger. However, charger is also part of vehicle in case of onboard or offboard. Similarly, the conductive immunity, high frequency fast discharge, so it should be of 2 kV. Voltage surges, it may be 1.5 to 50 microsecond surges in 2 kilovolt. Similarly, it's a kind of radiated immunity. Immunity is a kind of your hardware components, or you can say your electronic components, should be immune from any external disturbances. Okay, so one of the, this is just example. Again, I just request you don't take it as a final. For the complete detail, please refer to the standards. It is just for demonstration purpose. So radiated immunity, let's say it's talk about 3 volt per meter as a kind of you know, power signal, and in the range of 80 to 100 megahertz, 180 to 100,000 megahertz frequency. So your device should be immune, right? So this is just example. Let's say 3 meter or 10 meter, we are creating a disturbance signal of 3 volt per meter, which is having frequency of 80 to 100,000 megahertz. Your device should not be disturbed with this noise, right? And that's how we define as your hardware is immune. We said radiated immunity, right? Similarly, the conducted emission. Conducted emission, I think you know that, right? Uh, when we have this circuit built, there are multiple region where noise is generated. Mostly it happens because of the switching, and the other part, for example, you know, loop inductances and uh, other elements, which is kind of adding or helping this noise to amplify, and hence it is important to, you know, filter this out, not to get you know, disturbed. So there are regulations you have to comply, and you should not you know, uh, emit emissions more than prescribed limit, right? So for conductor emission is for low range. If you see that it is up to 30 megahertz with the limit of you know, I've talked about average, so limit of 46 to 50 dB, right? Similarly for signals and controls. Okay. Okay, so going ahead, we'll very brief about charger. Usually AC to DC charger, we say slow or low power charger, which has been used in two-wheeler, right? And DC to DC charger, which is high power charger, we usually use for four-wheeler. Okay. So if you see here, we divide the charger into 3 parts: level 1, level 2, level 3, with the voltage levels here. So this is the AC voltage and the DC voltage. Power is up to 3.5 kilowatt is the level 1 AC charger. Similarly, if you go for higher, level 2 or level 3, it is more than 22, 22 4.3 and up to 400 kilowatt. Okay, and usually, like I said, for two-wheeler, the level 1 AC charger has been used, and if you see type of compatible charger is Bharat AC 001. Similarly, level 1 DC chargers are also there. Level 2 AC chargers, level 3 AC chargers, level 3 DC chargers. Okay. So I'll talk about two-wheelers again. Okay. Moving ahead, typical charging system. Uh, why this slides is important? Because we are increasing the charging system in India. It is important to know what type of chargers are there. Okay. I'll talk more of the charger design in my second session. In first session, I'll just covering it very brief of charging system. Charger. Okay. Simple charging system. We say AC input, then we do rectification. That means AC to DC. Then we do the power conditioning. Let's say power factor conditioning. This become you know, AC to DC, still DC, and then we convert DC to AC, and then we do that inductive coupling. That means it will transfer where we you know, change the level of voltage as per required. I'll talk about, and then secondary rectification and battery. You see that there are close to 3 level of power conversion is happening from AC to DC, again DC to DC, and then DC to AC, then AC to DC. However, in between there is a AC to step up or step down, and then AC to DC. you can see there are 3 to 4 level of charger power conversion is happening. Uh, Again, it's a two-part, isolated and non-isolated. Very simple. When we say non-isolated system, we have directly all those 3 levels of conversion: AC, then AC to DC, the rectification, then rectification from the power factor conditioning, and then we again do DC to DC, and then battery. So if we don't need that isolation system, we can go through that. But it is not the case. We need the isolation system. Hence, we need to isolate the grid to the charger, that to the battery with the certain means. Okay. In this case, it is showing that a transformer has been used. So transformer is kind of used to isolate the system from the grid to the battery side. Like I said, charger I will talk more, and in my second session. Okay. Brief, I'll talk about charging infrastructure. Okay. If you see here, this picture has been taken by the Niti Aayog handbook. Battery swapping system is going on. What is battery swapping system? That means you can use your battery. You don't have to charge this battery your vehicle in the any charging station. You go to the battery swapping station, change the battery with the existing charge battery, and pay accordingly, right? And this is very easy and quick. The way you go to the fuel station and get your vehicle fuel in no time, the same way, because even you go for very high or fast charging, there are certain time, at least even not less than 20 minutes to 30 minutes you have to spend there to charge your battery, depend upon the battery capacity, right? So this is the one way you can kind of increase the, or you can say reduce the dependency of charging time, and use your swappable battery to run your vehicle and run your business. Second side I'm showing is the different public charging. If you see, there is a one charging you can have at your parking, at your apartment or your home, right? When you have this special charging infrastructure, right? Second is that you can have the multiple charging with your bike. Okay. So at least multiple cities, they are coming with the charging infrastructure, and it's growing up. Being in Bangalore, multiple apartments, even my apartment, have come up with the charging stations, and it is growing. And trust me, they are going to have some regulations for each and every apartments as well, to have the mandatory charging station to boost the electric vehicle into the India. Okay. So coming to that, the charging station, it is important that when you charge it, the way you charge it or the way you get the fuel, if you remember, when you get your fuel refilled in your in the fuel station, you can see that how much liters is filled, and accordingly it is charged, right? So that metering system is already there. So for charging your vehicle also, in the at the some extra infrastructure apart from your home, this metering system has to be there, and that's how multiple things has been already come up, and it's growing. So when you charge it, you have to have this charging point operators. Okay. These all the charging point operators has to be connected through some means to the cloud, and also the payment gateway, so that when it is charged, you must get all those information to your app or mobile or in your system, so that you must monitor how much electricity or how much energy you have consumed while charging, and hence accordingly you pay it. That's how we say it's a centralized management charging system, and it is rapidly increasing, right? So with this, I would like to close my part one session. I will be happy if you have any questions, and I'll try to answer.
Sir,
Yeah,
Avinash sir,
Yeah.
some of the participants, they have raised the doubts.
yeah. So
Uh,
so I just
shall I put them?
yes. So we can put those doubts, and we can have this small break for 2 minutes or 3 minutes. It's a bio break,
Okay, sir.
and then
Okay, sir.
we'll consider. Yeah. So you can
Okay,
have
sir.
this questions.
Okay, sir. Take a break, sir.
Yeah. No, we can let me answer the questions, and then
No,
we'll go
okay,
for
sir.
break.
Okay, sir. Dr. Bindu is asking, what is the minimum percentage SOC limit?
Okay. So this is a very good question. I'll tell you. Usually, when we say 0% SOC, there is one is the display SOC versus actual SOC. You cannot have actual 0% SOC. However, we always say 0% SOC, but just to consider that battery is having an internal battery management system. If battery is completely drained, this battery management system won't work. Mostly many batteries also having some type of monitoring system connecting with the cloud and some buzzer or alarm. So to answer this question, display is SOC, display SOC is 0%, but actual SOC should be 2 to 3%. That we say reserved SOC, right? The way if you see that in our vehicle also, when we say, we have some type of way that we say reserve, so that we put as a reserve system so that we can go or we can ride till vehicle or fuel station, right? So the same way, battery SOC, there are some reserve SOC that has been kept. It is not control of generic user, basically, just to run that. So battery, when it's a 0% SOC, before going into the deep discharge and before going to the hibernation mode, uh, there are certain protocols has to be followed, and it is there. I'll tell you. Number one, when it is 0% SOC, your vehicle won't run. We cannot take power to run the vehicle. That means you are kind of actually you cannot use the battery, but battery won't die. It is going to be in the deep discharge mode, so that you can you can charge your battery. And even you're not charging your battery, for example, you are leaving your battery, or you're going for vacation 2 or 3 months and leaving your battery is SOC of 0%, that will go to the hibernation mode for quite some time. It will be supporting probably a month or two. Yeah, I hope I have answered your question.
Yes, sir. Yes, sir. Same person, one more question. While discharging and charging, what is the C rate range?
Okay. Again, this is depend upon the battery manufacturer. So I remember that Professor Keshri was showing that typically when I'm showing as a 4.2 kilowatt hour or 3.5 kilowatt hour battery, and if you see that some of the slides have shown that 4 to 6 hours of charging, you can calculate it. Let's say if I have 3 kilowatt hour battery and we are taking charge of time of 4 hours, you can think of that how much current we are pushing, right? One C, it is a kind of 100% current. Let's say 3.4 kilowatt hour battery with the ampere hour of maybe it may be close to 40 ampere hour. That means for 1C, 40 ampere, if we push it, it will take 1 hour to charge full. But again, the problem is that if you push for 40 amperes, your overall conductor or conductive element or mechanical fixtures may not support. It may be overheated, right? So usually it is limited. It will be 0.2C to 0.3C. That is the usual practice for the normal or slow charging, has been practiced by the industry. But for fast charging, it may go for 1C or 2C also, but it is not recommended.
Thank you, sir. And next question is from Dr. Charu Kamecha. We've seen some of the recent cases in which vehicle catches fire during driving. Can you give some reasons for it?
Okay, so see, I'm not the right person to analyze or give some reason, but definitely catching fire is a very unfortunate incident. There may be multiple reasons. I'm using the may because what exactly the reason I don't know. but there may be multiple reasons. One is that thermal runaway, right? It may happen because of ambient temperature may go high. Maybe because I remember that if I see one of the video, it was kept in the sun, so maybe ambient temperature may go high, or cooling system may not be enough, or maybe certain fault may be happening, right? Usually, when the battery manufacturer or battery designer, when they design the battery, they take care of all worst case conditions, all worst case environmental, or you can say ambient temperatures. If you talk about, let's take example of summertime of, let's say, Rajasthan, or I think in some part of South India, in Nellore or somewhere, where the temperature is going 50 C, right? So 50 degrees C is the ambient temperature, and your battery temperature, if you are running, if you are putting the vehicle, if you're going to, let's say, 20 degrees C of rise, that means your battery is going till 70 degrees. Usually, all the battery manufacturers or battery researchers, they take care of all the worst case conditions. They do all the safety tests, and they make sure that battery should withstand till all worst case condition and should not catch fire or something happen, and then only they go for production. Even for compliance, let's say I talk about ARAI or something, they also make sure that battery is safe for customer. There are certain incident happen, I don't know, we can say is a type of accident, but exact reason that I cannot comment.
Okay, thank you, sir. One more query from Mr. Rajendran. What are the main troubleshooting you can impose on revolt motor bikes?
uh, if you talk about troubleshooting, it all depend upon what is the problem, right? So troubleshooting is a way to remove the problem. So before that, you have to understand what is the problem, what is the issue. Let's take example of charger, right? uh, let's say charger is not working, correct? So there are ways why we can find out. We can do the RCA. We say root cause analysis. There are 4 or 5 W's you have to follow, and accordingly you have to narrow it down what may be the exact problem, right? So it start with the human handling, how we are using the charger. Second is that what is the operating condition, or maybe what may be happening. You have to inspect it. You can also open it and see each and every component, whether each and every component is in the right condition and the right specification. Then also you have to see about the softwares. Okay, so these are the certain way that you can implement, or you can rectify the problems, you can troubleshoot.
Thank you, sir. Last question from Mr. Shishir Patel. What are the parameters related to motor to make it work in a proper way?
There are so many parameters for the motor. First parameter is the actual speed. Usually we take the speed. Okay, so uh, the best way to do that with the feedback speed, and then again voltage and currents. You must measure the right voltage and the right current. That means accordingly your circuit or sensors should be designed to give you the right voltage and right current. Okay. So these are the 3 parameters, and definitely all the rest of the parameters you are calculating it internally, and accordingly you are generating the signals and PW, and then finally your voltage and currents are generated.
Okay, thank you, sir. Thank you, sir, for your kind explanation and patience to answer the questions. Let's have this bio break of 5 minutes.
Okay.
Again, we will continue the section, sir.
So 11:44, we will be back by 11:50. Sharp
Okay, thank you,
11:50, I'll
sir.
be back.
11:50.
Thanks.
Participants, please rejoin by 11:50. We'll have the bio break for a span of 5 minutes.
Hello. Hello, sir.
Welcome back, sir,
Yes, sir.
for this break. Please continue the second part of this today's section, sir.
Sure. Sir, please make me host. I'm not able to share.
Yes, sir. Sir, you can check it now, sir. Okay.
Yeah, yeah. So I'm audible, right?
Yes, sir. You are audible, sir.
Okay, okay, fine. So see my screen, sir.
Yes, sir.
Okay, okay, sure. So thank you, everyone. I believe that last session was informative. I tried covering some of the aspects on a very high level, so that you get the idea that what's going on the EV, and definitely please feel free to connect me or any of sir here, and the participants, or maybe I think many other Professor Ritesh and similarly the experts are there. You connect any of your students. I'm happy to answer any of your queries. Please do so. So second part, I will be covering charger, where I am using my expertise to do. However, when we say charger, I'll just want to give a brief that uh, there is a little difference between when you do the actual research and when you do the actual product design, right? Because we are doing the product design for electric vehicle, I will cover that aspects and what are the challenges we are facing while designing the charger, while making the product into the market, so that you can get that flavor, right? And that also you can see that how your research work or your knowledge work can be useful for developing as a product, right? So this charger design I am going to cover it. Okay, to start with the design challenges, right? We When we start, right, or any product, let's take about the charger. What actually you see as a development, right? First you start with what may be the input voltage you are looking for, right? What are the isolation requirement? What are the digital control? Digital control is important here. We are talking about the PFC LLC that I'll talk about. What is the PFC and LLC? And then important is the efficiency optimization. Your charger or your controller should not only is a very good control. Efficiency is important. Efficiency in the term of the power efficiency, right? Other part is the safety. Why I have put as a grounding need? Because you remember that I have talked about EMIMC, right? So when we talk about EMIMC, this is very important. Then packaging, how it looks like, now how robust it is, because you are not going to use it at your home as a vehicle. You think of, you are driving at 100 km/h, right? So all your components, which is integral part of your electric vehicle, should also be that much of robust. It should not be you drive it and maybe some some disconnection, some of the fault, or maybe some mechanical damage or electrical damage, or let's say talk about soldering, desoldering. All the things should not be happen, and not only for one. You know that you are going to use this vehicle for 5 years. Let's talk about all your components should also be withstand along with the vehicle for 5 years, and then only your vehicle are robust. right? So that is important. So going ahead, let's take example, input voltage range. What may be that, right? So as an input grid, we say we want our charger so that if our voltage range is 160 volt or till 300 volt, our charger should work. So accordingly, you are going to design all your components, right? Isolation requirement, 6 kV. This is just an example. Let's say 4.5 kV is enough or 6 kV enough. Digital control. Digital control, that means all housekeeping, all master control, all communication should be intact, right? When we say talk about PFC, to optimize, you must have a very good ZVS, zero voltage control, and highest power factor, etc. Efficiency, it is important. Grounding need, you know that there are power ground, there are control ground, there are earth. So you all have to consider these three, and you have to put enough isolation between these three. Packaging, like I said, handy, and cooling requirement, right? And robustness, like I said, when you are giving the warranty of 3 to 5 years for your electric vehicle, all those accessories, all those components, hardware components, should also need to be that level of robust to support 3 to 5 years of life expectancy, right? Moving ahead, charger topologies, right? I'm going to show you mostly commonly used for the charger for the uh, level 1 charger. I hope you remember that level 1 charger, which is up to close to 2.2 kilowatt. That is used for mostly normal, or you can say slow charger for two-wheeler application, right? So this is is the most commonly topology have used is PFC LLC topology. Right? I'll just give you one very brief for other topology as well, but I'm going to talk about in detail for the charger PFC LLC topology design steps. Right? If you see here, we are having the input of AC, then we must have some common mode filters. Changing this AC to DC with the help of rectifier, we say bridge rectifier, and then we are boosting the voltage. So if you say here 100 to 200, let's take example of 200 voltage input. Changing this AC to DC, it will be close to 200 volt DC. Boosting this voltage, DC voltage, along with the power factor controller, PFC controller, till close to 400 volt, and then we'll have the LLC. This is the kind of, we are converting from AC to DC, this half bridge inverter, or you can say pulsed DC, this DC to pulse DC, so that it will be type of AC. And then we are putting in a resonant tank here. So resonant tank is nothing but L, and C, right? And then converting this AC here to required, stepping up or stepping down depend upon this transformer. In this case, it's a 400 volt AC. We need here, let's say 848 volt, or let's say 72 volt, depend upon what is the battery. We are stepping down, and secondary, we are using the synchronous rectification to control it. Okay. So now if you see that we are only having the power 4 stage of power conversion, AC to DC, then DC DC, then DC to AC, then AC AC, then AC to DC, correct? But now if you see that this looks very simple, but what is the accessories for this? We have so much of filters, common mode filter here, common mode filter here. In the mean of, there will be multiple filters, let's say DC link capacitors, there are multiple other filters. And then overall, we'll have this PFC controller, PFC LLC controller, and this SMPS controller. SMPS is for, uh, housekeeping supply. And overall, the isolation, because this particular transformer is isolated from the power side to the battery side, we must have all those feedback circuit isolated from the secondary to the primary, right? So we can use as optocoupler to maintain the isolation between the primary and secondary. So this is the simple. I'm going to talk about in detail for this LLC topology and the charger details in detail. So stay tuned with me. Okay. Coming to first part, what is the PFC boost converter? Okay. PFC boost converter and why it needed. Simply, we are converting AC, rectifier and DC, right? What we are doing here, if you see here, we are using the L, this is the inductor, okay, and we are using a switch as a MOSFET with the forward diode here, and and some filters to the right side, right? By the means of a reference current, we are kind of switching it here, and accordingly we are boosting it. Right? Question is that why we need power factor conversion? I think many of you might be knowing, but whoever not know, just I'll give you. Simply, if you don't use a PFC converter, when we converting from AC to DC here, what will happen that this is converting directly this type of secondary side voltage. This is the AC. This is AC input, and secondary side voltage will be like this. Okay, that means it is AC basically. Secondary will be this and this. But if you see that the load side, the waveform, or you can say the how the input AC current will look like, because of this capacitor, this filter capacitor, which is used the secondary side. When this is charging it here, okay, so in the form of charging, this capacitor is charging. When this capacitor is charging, at that time only the current from the AC is pulled, right? So while the capacitor is charging, the capacitor current is pulled, right? When this capacitor is discharging, there is no current is pulled by the from the AC input, right? So if you talk about one complete wave here, the input current which is taken by the input side is like this, okay, right? Now if you compare this as a voltage and the current, this is not in phase, right? Because of this voltage and current is not in phase, we can say the power factor is very poor, correct? So because of the power factor is very poor, there are certain other issues may happen to the grid side. And as a source, as a power source, or you can say grid, you need to maintain the power factor. Otherwise, this is the burden to the generator. That means you are having so much of reactive power here, right? So to make this as a power factor, you must align this current with the voltage, right? And how you do that? To do that, we need certain this type of arrangement, right? So that you make the reference current in phase with the voltage, and then you do the switching this particular MOSFET at very high frequency, so that this current should be divided, or you can say divided as a pulse like this, and it can be distributed like this. And average of this current will be like this. So now if you see here, this current and this voltage in phase without changing the power requirement. Okay, so if you calculate the overall area of this current, or you can say overall current for this particular time, and if you calculate this both should be the same. Okay, so that's how we need the power factor correction. Ultimately, we are boosting the voltage here, and we are getting the voltage almost of 400 volt. If you see, come here again, we are boosting this voltage till here before this half bridge, and close to 400 volt if you are going to 200 volt AC. Okay. So depend upon that how you are switching it, this particular current power factor operation divided into three parts. One is that continuous current mode. In the continuous current mode, this red line is nothing but reference and this blue is actual. If you see that the current is always, because of the switches, the current is having this sawtooth wave, but is always, close with this reference current, and none of the current is going to zero at any moment. Okay, so we can say this is the continuous current mode. While in discontinuous current mode, to the right side, if you see here, at every switching, the current spike is touching the 0 point. Okay, at every point, if you see there, we can say it's a discontinuous current mode, but average current will be this. And this critical conduction mode, it is every spike, the current is coming to 0, but not staying for a momentarily. It is 0 and it is again coming back like spike. It's called a critical conduction mode. Okay, there are certain advantage and disadvantage of these two. Let's take of the continuous current mode, what it takes and which one will be better. Obviously, continuous current mode will be better as compared to discontinuous current mode. But what it takes? It takes as the bigger size of inductor, this inductor. Okay? The bigger size of inductor, so that means you have to have more cost, right? In discontinuous current mode, because the energy stored, if you see this part is the energy stored, this part is energy stored is lesser, so inductor size is smaller as compared to continuous current mode. But again, which one, what it takes the more ripple, if you see here, correct? So in this case, you have to depend upon capacitor size, right? More the ripple, you have to increase the capacitor size. So now it is understood that it is the trade-off between the inductor and the capacitor. Okay, so that's how we design it. So this is just a snapshot of DCM versus CCM. Like, more power handling capacity if you want, you must go for CCM. If you need less power, you can go for DCM. Okay. Coming to the Emi Emc filter choke, it is important because when you are using the PFC, there you must have that input side Emi Emc filter, right? So this particular snapshot showing that a choke, there are two chokes involved here. This choke we say common mode choke. There's another choke is a common mode choke. This CY is nothing but Y capacitors, okay, and this CX is called X capacitors. This particular resistance, this is called MOV, metal oxide varistor. This MOV is used for limit the any input transient or surge. Okay, X capacitor is used for differential mode noise, right? Common mode is used for common mode noise. Similarly, Y capacitors are also used for common mode noise. This is assisting this common mode choke, right? And finally PFC. So this particular arrangement of filters are important while doing the designing the power factor PFC basically or charger. Okay. Usually a snapshot of PFC control here. Simple. Like I said, there's the input voltage. When it is filtered, we'll have a DC voltage here, and then we'll have this inductor, MOSFET, secondary diode, and this load side. Okay. What you do here, you take this reference here, this reference, and this reference here. What you do that accordingly, it is generating the signal, right? And actual current you take. So based upon this voltage reference, you are kind of generating the current reference here, okay? And accordingly, you are switching the MOSFET, right? So this is how the simple control of the PFC. Okay. Coming to LLC control. Before LLC, we must know that, what may be the half bridge or full bridge. Okay. Here I am showing the full bridge, LLC. Okay. However, I have written a half bridge. I am showing the full bridge. In full bridge, if you remember carefully, we are getting a DC signal here. Just let me go back here again one more time. If you remember here, this half bridge or full bridge, right now I'm showing the full bridge. This particular point, after boost PFC, we are getting the DC signal here. Okay. We are getting the DC signal here. By the arrangement of these 4 switches, S1, S2, S3, S4, we are getting AC signal here. Okay. Once we are getting AC source, AC waveform, we are converting from this particular primary side AC to secondary side with the mean of primary and secondary turns ratio, what with the desired voltage, and then finally filtering out. We can use a MOSFET also, we can use diode also here to filter it out. Okay. So this is a simple topology of LLC, but operation is not simple, right? Why we need LLC, right? The answer is to have the maximum efficiency. How we are going to achieve that maximum efficiency? By the mean of zero voltage switching, right? And to achieve the zero voltage switching, we need this resonant tank, right? To make sure that switching is happening at zero voltage to achieve maximum, or to reduce losses to achieve maximum efficiency. Okay. So I'm going to talk more on this. Let's say, please excuse me, this is a full bridge. I have written half bridge. This is a full bridge. Start with, we need to have this converter gain. Right? What will be the converter gain? We'll have this switching bridge gain. This is, and then resonant tank gain, transformer turns ratio. This one. Okay. So finally, we get that final this overall converter gain. In case of full bridge, this switching bridge, if it is full bridge, this gain is 1. In case of half bridge, this gain is half. Right? Because for full bridge, we are getting as a complete positive and negative. Half bridge, we are only getting the positive side of pulse. Okay. If we convert this as a resonance, let's take with the VAC in this point, that means as a pulse voltage. Now, if you see that frequency of this pulse voltage is important, that means frequency, switching frequency we say now on we say as a switching frequency, right? Fs, switching frequency, Fs. Okay, we'll have CR, LR, and LM, these 3 passive components, which is creating a resonant tank. This LM is magnetizing inductance, LR is resonant inductance, and CR is resonance capacitance. Okay. For resonant tank gain, there is a 3 factors associated with that. However, this complete things is written in this equation. Okay, I'm not going to talk about the equation, but if you see the factor here, this Q is the quality factor that depend upon this LR, CR, and this load. What is the load? Okay, and then normalized frequency, Fs and Fr. Fr is a resonance frequency. It is important. Fr is nothing but 1 by 2 pi root under Lc, and M is nothing but primary to secondary total inductance. Okay, so this equation just keep in your mind. This is the equation, this K factor, and while designing the resonance, this is important. Okay, so because this is a resonance and it depend upon the switching frequency, you know that this passive elements, this inductor, capacitors, and LM, that behavior is depend upon the frequency, what it is going on, and accordingly, you know that how the resonance works. Okay, so the quality factor, if you remember this formula, okay, the quality factor M and the normalized frequency of Fx. Okay, I've already written here, and if you plot it versus the frequency and this resonant tank gain here, you see that different type of plots here. Okay. In this plot, we divide this into two parts, or in fact 3 parts. One is that this side is the capacitance, capacitive gain, and rest of the part is the inductive gain. And we have to decide where we are going to keep our, the gain. Usually, we don't keep the gain in the capacitive. We try to keep the gain in the inductive. Okay. So now you understand that to achieve that 0 voltage switching, we have to achieve this gain here in the inductive region, this side, right? So once we decide where is the operating gain here, accordingly, we decide what is the quality factor we want to achieve. For example, take here green line where quality factor is 0.5. That means if you want to put it here, we know that quality factor is 0.5, and normalized frequency, switching frequency you decide from here, and accordingly you calculate what may be the LR, what may be the CR, and what may be the LM, right? So now you should know the characteristics of your operation, your reason, and accordingly you decide what may be the resonance frequency and what may be the CR, LR, and LM. And accordingly, you design your LLC transformer and select your capacitors. Okay. When we operate, so now we, like I said, we have this resonance frequency and the switching frequency. Depend upon the resonance frequency and switching frequency, we say at this point, when we say resonance frequency and switching frequency coincide, but because we have to go to the inductive region here, we have to keep our switching frequency above resonance frequency to make sure that our LLC is operating above this region. That means operating in the inductive region, right? We cannot operate our LLC in the capacitive region or below resonance frequency. So we have to make sure that switching frequency should lie above resonance frequency. Okay. Let's talk about the mode of operation in the power delivery. Okay. This is a resonance act. When it is on, let's take one cycle. When it is on, power delivery is going from S1 to all the way LR, LM, and it's going here. And accordingly, the secondary is getting excited and we are getting the DC voltage. Correct. Once 0 switching voltage is achieved, what is happening that if you see that this inductor basically it is kind of flowing in the opposite direction. In spite there is a positive voltage applied here. Okay. In the freewheeling operation, when positive voltage applying, this resonance capacitor is conducting, and with a negative voltage, this is conducting like this. Okay. So in detail, I'll just tell you, this is a little bit of complex. In detail, we have 3 modes of operation. One is resonance frequency, one is above resonance frequency, which is this inductive region, and one is below resonance frequency, which is capacitive region. Okay, like I said, let's take example of when it is operating at resonance frequency. If you see here, when switch S1, S4, and S2, S3 is working, that means S1 and S4 is on, S1 and S4 is on, S3, S2 is off, this is on. So voltage across diode is on, right? And current through inductor is like AC, and current through inductor through magnetic is like this. It is increasing, it is getting charged, correct? And diode is like this, and diode D1 and D4 is conducting. That's the secondary side, right? The first cycle. And the second cycle, when it is switching from S1, S4 to S2, S3, the secondary side, when secondary side is on, the transition between first cycle and second cycle is important. Why? Because always we are trying to see that zero voltage switching, and that's how all arrangement has been done. This transition between first cycle to second cycle, you have to look here. Okay. At resonance frequency, if you see, it is transitioning, and this is a good. Basically, if you are able to achieve this is even more optimized. Okay. Above resonance frequency, if you see here, when we are transitioning from first cycle to another cycle, when it is going to zero, this current is going forced to here, right? And this diode voltage is coming forced down to zero. Correct? So at this transition part, there will be very less losses, and hence, even in spite of high frequency, the losses will be less. Okay. While if you see that above resonance frequency, if it is going all the way between first cycle and second cycle, if you see when transitioning from the resonance LR versus LM, there is a certain mode of operation here, will have the more losses, right? So I'll just go through one more time. I believe this is a little complex. Okay. At the resonance frequency operation, we have that each cycle, half cycle, completes power delivery operation. Okay. The resonant half cycle is completed during the switching half cycle. By the end of switching cycle, first cycle, what will happen that ILR reaches the magnetizing current. This ILR and ILM will be equal here, and the rectifier current is zero. Then secondary side rectifier current is zero. Okay. In this case, resonant tag has unity gain and best optimized operation. Right. So if you talk Fs is equal to L at resonant frequency is the best test optimized, but achieving it's a little difficult. So we are going for little higher side. Okay. Secondary when we say operating a resonance more than switching frequency more than high resonance frequency. In this case, first half cycle is not completed, right? Resonance is not completed. First half cycle, the resonance half cycle is not completed and interrupted by the start of the second side. Okay. So what will happen in this case? Primary side MOSFET has increased turn on of losses as compared to resonance. Correct. Now coming to the operation below resonance, what is happening there? The free will, in this case, what is happening that free will operation is happening, right? Starts and carries onto the end of the switching half cycle and primary side. So what will happen that primary side conduction losses will be more because of the circulating energy. Right? So if you see as a comparison, at resonance frequency it is high, very good operation, either at resonance frequency or little higher than resonance frequency. That is the most optimized way to operate. Okay. So the design steps we need to follow while doing the LLC. First, we select that what should be the Q max, Q quality factor, if you remember, right? And then what will be the M value? Then see that the normalized frequency Fs by Fr, what will be the minimum and maximum? And then you see whether we achieve the required gain, yes or no. If no, that means you have to increase the value of M continuously so that we get the normalized frequency at the minimum and K as a maximum. And finally, when you got all the value, you go and select the resonant passive elements LR, CR, and LM, and accordingly you go and design it. Okay. One example I'm showing here for LLC controller. Okay. This is example of Infineon LLC controller directly, just to showcase to you guys. Okay. Here, if you see that this LR, this is half bridge connected. This is half bridge. We have connected LR, and this LM is part of this inductance transformer, and this CR. Okay. And the secondary, there are MOSFETs are connected. We say synchronous rectification to the secondary side. Okay. And as a feedback, we are measuring the voltage here. Okay. With this voltage regulator and the optocoupler, we are sending the voltage to this, and we are setting up the reference voltage here, and internally it is having the calculations. To have this supply, we are giving a voltage source here, VCC. Okay, and this VCC we are getting from the high voltage side. This HG and LG is nothing but high side gate and low side gate. This is the high side, and this is low side gate MOSFET, and drive. This is the gate driver. Okay, and input is the current sense. This is the CS, nothing but current. So this is the one example of LLC. Okay. Now, designing is one part as only the control side, but what are the others? Is that enough? No, it is not enough. There are other parts associated with that while doing the design. Okay. What are the other parts? When we design the charger, the safety challenges is important, right? Battery cell temperature, battery SOC, battery overcharge, pre-charge, hibernation, all those battery operating conditions. You'll be wondering that while charger, how we are getting these information. So that's I'm going to talk about. This what we are getting this information from the battery using the communication, either RS425 or CAN, and that's how the battery smart battery has to design. Okay. And then important input surge current, because the input side capacitor is connected. When you start from the power grid, it will take a really high surge current, and you have to design the surge current arrestor or some type of limiter to deal with that. And the battery profile CCCV I have already talked about. Your battery charger should be enough. Like I said, this should always take care of the CCCV and the battery charger side over voltage over. Let's say if your charger is getting over voltage or over current, all these protections and the ambient temperature to talk about, right? So how, when you design the charger, you must know the battery cell, right? You must understand the battery cell characteristics with the data sheet, all their SOCs conditions. What are the over voltage, pre-charge, hibernation? That means all the cell behavior. Input surge current, you must understand. Battery CCCV mode, over voltage, over current protection, and the ambient temperature. Second, very important is that compliance, right? I have already talked about that when you design the charger or any hardware, one thing is important you have to think of when you are going to make production. You must know that what is the compliance, otherwise it's not allowed to sell. Emi Emc compliance is very important. We have that radiated conductor, bulk current, radiated immunity, then mechanical environmental, right? Ambient temperature, dry heat, ambient humidity, insulation, cold condition, and that certain test you have to do, right? Important is that, like I said, communication. This is the most important part when you design the battery charger. It must communicate continuously. This is a parallel communication while doing all those control, continuously monitoring the battery's SOC cell current, etc. Okay, and then what the challenge for battery or any hardware? Always we have to go for cost optimization. right? When we go for the cost optimization, we have to also to do that, combination of topology to have the wider range, cables, connectors, semiconductor high lead time, right? Many of you might be knowing that semiconductor shortage is affecting many business, not only EV, all electronic business. Go for testing for mass production. Important product failure. When you design it, you say very robust, but you don't know what is the customer behavior, right? So you should understand what type of customer you are going to sell your product and what is their behavior. Accordingly, you have to make. You cannot blame to the customer, hey, I told you not to use like that. They will just behave. I'm used to do that. So you have to protect your product and to make this necessary protection arrangement to address such difficult customers, right? And this is important that poor quality in India, especially in the poor uh, urban or semi-urban areas, are very poor, and you have to deal with that. And then service repair challenges, critical part availability. Yeah. Okay. And important is that technological advancement. What is happening that wideband gap, it is already there. We are evaluating GAN, SIC, etc. Right? Multiple other topology, for example, PFC, interleaved, etc. Optimized control strategies, cooling methodologies, and advanced simulation platform. Always look into that, right? So, like I said, all those materials what I have taken is available online. Some of the things I have taken from Niti Aayog, area reference material, Infineon application notes, and many others. Feel free to discuss with any of us. Yeah. That's all. That's the end of my session, and thank you very much for your uh, listening. I hope this is being informative for you. Please feel free to ask any questions. I'm here, or sir, professors are there. Uh, yeah, that's all. Any questions, please go ahead.
Thank you very much, sir, for very broad explanation related to the present scenario in the maintenance of the electrical vehicles, particularly infrastructure related to charging systems, control units, compliance standards, particularly.
Yeah.
We got good information related to the compliance standards and the charger design, and most important is safety challenges related to battery maintenance. Thank you very much, sir. Some of our participants, they put some more queries. Professor Subramaniam sir from our institute, he is raising a query. What is the lifespan of an electric battery? He is asking.
Okay. Say this is I would say it's a very difficult question, but I'll say that most of the battery manufacturers, they are giving the warranty of 2 to 3 years, because that depend upon, however, battery life is depend upon the charge and discharge cycle. Okay, how fast you are charging or discharging. Okay, that's how battery life degrades, but depend upon the overall scenario of the user, that how, because we cannot say like one person is using, let's say one person can drive the vehicle all the day, right? And one person may driving only weekdays, and one person only driving only weekends. So on an average, if I say as a customer scenario, at least 5 years are the battery life. However, I'm just talking about the uh, depend upon the customer. It's not a technical thing. Battery life is depend upon the charge and discharge cycle, right? As a technical answer. But in India, depend upon the various customer profiles, various uses, it is typically the life is from 3 to 5 years.
Thank you, sir. One of our student, Mr. Srikar, is putting the question, what is the effectiveness of electric vehicles in hilly stations or hilly areas?
Okay. This is again a good question. Really good question. Thanks for putting this question. See, the hill areas having the different operating condition, or you can say environment. Number one, when you go to the hill areas, the roads are not straight. They're having some kind of inclination, correct? So if you see that when you are driving your vehicle on the ramp, right, that is having more, you can say, a stress on the motor and the battery. You need more power and the torque, correct? And you cannot reach the speed of let's say your battery or vehicle is able to achieve, let's say, 80 or 100 kilometer per hour, and the vehicle in the hilly area you cannot achieve it. So that is a difficult road situation or difficult running condition for the electric vehicle, of course.
Thank you, sir.
Yeah.
And Ms. Himindu is raising a query. Mention the advantages of public charging stations compared to the private charging stations.
Okay, so I have already shown you that
Is there any
public
difference?
there is no difference of public charging station versus a private charging station if you are going to have the normal charger. For example, you said that I am going to use a simple charger. So either you use at your home or as a public or as a as a government or private charging station, it will be the same because it all depend upon the current rating or voltage rating, right? Only one difference is that at home you are not paying, your billing is from your normal meter, electricity meter, and there you have to pay a little higher amount. That is only the difference. However, some of the vehicle has come out with a two type of charger. One charger is normal charger, one is a fast charger. I think some of you have asked the question that what is the fast charger. Normal charger what we use at home is let's say 4 to 5 hours of charging. Same thing can be used in the private charging, but when you go for the you know fast charging, you can charge it in half an hour or 1 hour, correct? Accordingly you are paying, but that charger is having more rating, and but your vehicle should able to take that fast charger. I hope you understand. Let me take one more in example. Let's say you buy the vehicle, right? You have to ask the question whether we can go for fast charging or not. Your manufacturer will say, you cannot go for fast charging. Then you cannot go for fast charging because your vehicle is not designed for that.
Thank you, sir. One more query, sir, from Mr. Rayappa Srinivas. Sir, lithium ion is costly material. Can you use any other alternative material in place of it?
Say, I'm not the battery expert, so I cannot comment. I'm a hardware guy, so I can comment on the hardware side, charger or controller side. For battery expert or battery material expert, I believe I think you should connect with some battery expert guy. But I know that there are multiple materials are available like lithium ion and LFP and all those things. So I cannot answer on this question. Sorry for that.
Okay, sir. Thank you, sir. Sir, what is your opinion about hybrid vehicles, sir?
Okay, hybrid vehicles are a combination of electric and IC engine or maybe others. Hybrid vehicles are most successful in European and USA side. The reason is that hybrid vehicles can you can use as a really long drive as well as city commutation, and you don't have to depend upon electric battery all the time. For example, let's say electric vehicle has a limitation of only the electric battery, right? But disadvantage of hybrid is that will be too much of costly because it's like you are buying your normal IC engine vehicle along with the electric engine vehicle. So both are clubbed into one vehicle, right? So it will be very costly. because it will have this electrical system, battery and everything along with the IC engine, something like that, right? So it will be costlier than either of these vehicles. So in India, it is not successful, of course, but in Western countries, it is successful.
Okay, thank you, sir. Thank you for your patience to answer our queries. Thank you very much, Mr. Avinash Kishore sir, for sparing your valuable time for this today's section. And please wait for 5 minutes, sir. Our students wants to interact with you. We
Sure.
are changing you to other room. Meanwhile, I will address the participants.
Yeah.
Thank you, participants, for this today's section. Those who didn't receive ID number, please refer the chat box and send your details to mail ID nrsrak@rediffmail.com. We will alert the ID numbers. Then we will share the link also for feedback. In the feedback, ID number is to be posted. And for tomorrow section, we'll start at 10 a.m. Dr. Rajat Kumar Sahu from NIT Raipur will deliver the lecture on recent trends and advancements in electric vehicles and charging station. Thank you very much.